second talk by Dapeng Mu from UNICAMP, stable pairs and connectedness for modular spaces, rank 2 sheaves on P3.
Okay, so first I would like to thank the organizer for giving me this opportunity. And this is also my first ALGA. So I'm going to talk about stable pairs and connectedness for modular space of rank 2 sheaves on P3. This is a joint work with Professor Marcus Jardim. And this is still in progress, so I will say some of the main ideas, and I will show you one example. This is a brief outline of the talk. So the first two sections are basically some concepts, definitions, and then some geometry will start to show up from the third section. Okay, so we work on a projective space P3, and then let me start with the Serre correspondence. So this is the classical one for rank 2 vector bundles on P3. So which says there's a one-to-one correspondence between the following two pairs. The first pair consists of E and S, where E is a rank 2 vector bundle. And then a section of E, I denoted by S. And then we require that the zero locus of S has codimension 2. And on the other side, the other pair consists of a locally completer section curve with an extension class, C. So let me put a remark. If E is rank 2 but reflexive, and then this Y is generically locally completer section curve, but it's still called Macaulay. Okay, so our motivation for this work is that we try to generalize this set theoretically Serre correspondence into a flat family, and we also hope to find some stability conditions such that we have a good modular space, so we can use the deformation of curves to study the deformation of sheaves. So that is, rank 2 sheaves. So this is the motivation. And then before giving you one more motivation why we use stable pairs, so let me put one more remark. So as we saw previously, we have to consider all torsion-free sheaves of rank 2, because if we only consider vector bundles or reflexive sheaves, then the corresponding curve is called Macaulay. But a Macaulay curve can deform to something non-Macaulay. So I will consider all torsion-free sheaves. And then let me try to say something about the motivation why we use stable pairs. So let me consider a pair, E, S, where E is a torsion-free sheaf. The rank of E is 2. And we pick a non-zero section. So the section gives us this project sequence, O going to E. And then I will denote by Q for the co-kernel. So for this correspondence to hold, actually we hope this Q to be ideal of some curve so that we have this correspondence. But sometimes this Q is not torsion-free. So for now, let me call such a pair a bad pair. So how do we rule out those bad pair? Suppose Q is not torsion-free. So sorry, I forgot to say, well, in this case, Q is rank 1. So it's isomorphic to a twisted ideal sheaf if and only if it is torsion-free. So suppose it's not torsion-free, and then let T be the maximum torsion subsheaf of Q, and then we have this following diagram. So in the diagram, we consider the composition going from E to Q to the quotient. So let me, so this is the composition, and then let L be the kernel. So indeed, this diagram gives us a subpair. So this diagram gives us a subpair, which is L and S1. So here by subpair, I mean this L is a subsheaf of E, and then the section S factored through S1. I will show in the next slides. We define such a pair as a subpair. So my point is, if Q is not torsion-free, meaning we have a bad pair, this pair does not correspond to curve, then we must have this commutative diagram, and then we must have this subpair of the pair E, S. So we want to find the stability conditions such that this subpair destabilizes the pair E, S. So that is the motivation why we use stable pairs. And then before showing some geometry, well, let me go through some concepts relating to coherent pairs and the stability. I think maybe you have seen some of those in the morning during Professor Schmidt's talk. So here I can make X more general. So here I'm assuming X is a smooth projective variety with some fixed ample class. And then I will say a pair E, S is a coherent pair if E is a coherent sheaf and the S is a section. And then this is the definition of a subpair. So I think this one and next one are all due to Huibich-Lan. So we say a pair F comma S1 is a subpair of E comma S if F is a subsheaf of E, and then S factor through S1. So meaning this commutative diagram holds. So here's a section of S. This is the section of the subsheaf, and then we have this commutative diagram. And then we call F comma S1 is a subpair. We can also talk about stability conditions for a pair. So for this purpose, let me introduce one more parameter, and I denote it by delta. So let delta be a non-negative rational polynomial. So meaning the leading coefficient of delta is positive, and all coefficients are rational numbers. And then this is the definition of a stable pair. So firstly, let me introduce the reduced Hilbert polynomial for a pair. So for a pair E comma S, we define the reduced Hilbert polynomial as the usual Hilbert polynomial plus a delta divided by the rank. So here, if the S we choose in the pair is not 0, and then we add this delta in the numerator. If S is 0, then in this case, there's no such a delta. And then in this case, it's reduced to the case of a sheaf. So this is how we define the reduced Hilbert polynomial for a pair. With this notation, we can define stability for a pair. So we define a pair E comma S is delta stable or semi-stable if for any subpair F comma S1, we have the reduced Hilbert polynomial of the sub is less than or equal to the polynomial of E comma S. And then let me quickly state the theorem. So simply speaking, a coarse moduli space exists for semi-stable pairs, but we'll need to fix a class, and we fix a delta. So here when I say a class for a pair, I actually mean the sheaf in the pair has class V. Okay. I think, so from now on, I will show you the general picture for walk crossings for the rank 2 case, and then we'll see some geometry. So from now on, I will go back to P3, and then I will fix a rank 2 class. And then, so for any such pair, E comma S, such that the class of E is the fixed class V, the section gives the Schritt sequence as I showed before, and then I denote by Q for the co-kernel. And then here comes the general picture for rank 2 class. Okay, let me explain this picture bit by bit. So firstly, we see there's an axis. This is an axis of polynomials. So every point on this line represents a rational polynomial. And then according to the lexicographical order, so one endpoint is 0. And then there's another point, which I denoted by delta 0, and then I write collapsing wall for that. So that means if you choose a delta that is larger than delta 0, and then there are no stable pairs with respect to that delta. So there only exists some non-trivial stable pairs in between 0 and delta 0. So these are, say, delta 1, delta 2, dot, 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 until the last one I denoted by delta t. And then there are 2 chambers that are special in this case, which is the first one on the left and the first one on the right. So I think we saw the case for a curve in the morning. So for any delta in this chamber, the moduli space for a pair is actually a fibered Giesecker moduli space, meaning for any stable pair E comma S in this chamber, the sheaf in the pair is Giesecker semi-stable. And on the other side, so for any delta in this chamber, so what happens is for any stable pair E comma S, this Q is torsion-free. So meaning in this chamber, we does have a flat family of pairs. So every one of the pair corresponds to a curve. Every sheaf corresponds to a curve. And this is what we want. So maybe let me put a quick remark. Our original goal was to relate Giesecker moduli space to Hilbert scheme. So here we found a relation with the help of stable pairs, but they're not directly related. Well, the reason is, so for instance, we choose a Giesecker semi-stable sheaf with a section, and then it's very likely the co-kernel is not torsion-free, meaning this pair does not correspond to curves. And conversely, if you choose any curve, the extension may not be Giesecker semi-stable. So here the picture we have is, so for instance, we start from this fibered Hilbert scheme, and then if we move from right to left, and what happens is every time we cross a critical point, some curves are removed, and some Giesecker moduli, some Giesecker semi-stable sheaves are added, until in the end, all the sheaves in the pair are Giesecker semi-stable. Okay, let me show you one example. So this is the first non-trivial example I work on, which is this instanton class 20-10. So I call it non-trivial is because, so let me go back to this picture. So I will say this class is non-trivial if there are some walls in between 0 and the collapsing wall. Or in other words, these two special chambers are different. Otherwise, if there are no intermediate walls, and then these two special chambers will be the same, and then I will call this case trivial. So let me show the example of this, this non-trivial class. I will show you in 2 steps. The step 1, I will try to specify these 2 special moduli spaces, which are the fibered Giesecker moduli and the fibered Hilbert scheme. And after that, I will show you what happens when you cross those walls. So let me start with the fibered Giesecker moduli. So due to this theorem by these 3 people, so we know for a sheaf that is Giesecker semi-stable with this class, if and only if E satisfies this Scherzak sequence. Sometimes I think people call those E null correlation sheaf. And then the theorem implies that the Giesecker moduli for this class is actually P5. And then since the first moduli is fibered over the Giesecker, and then I will move on to compute the fiber. The fibers are basically the global sections. So for those E, we can actually see there are no global sections. And then we twist the E by 1. There are some non-trivial sections. So we have to twist the class by 1. So you will see here, I denote by the moduli space, not with respect to V, but with V1. Well, the reason is if here is V, then the fibered Giesecker moduli space will be empty because there are no non-trivial sections. So here I twist the class by 1, meaning I'm defining V1 to be the class of E twisted by 1. So in this case, then the fibered Giesecker moduli space would be non-empty. So the theorem and those remarks will show that this first moduli space is a P4 fiber space over P5. And then let me move on to the other side, the fibered Hilbert scheme. So firstly, let me try to specify the curve. So this is the sequence that gives the correspondence between a sheaf and the curve. So a direct computation shows that the Hilbert polynomial of y is 2t plus 2. And then a theorem due to knowledge says that this Hilbert scheme on P3 with polynomial 2t plus 2 has 2 components, C1, C2. And then a general curve in C1 is a union of 2 skew lines. The dimension of that component is 8. And then for C2, a general curve is a plane conic curve, union a point. And the dimension of that is 11. And then let me move on to compute a fiber. Well, in this case, the fiber over a curve is this extension class. And then some direct computation shows that the fiber is either P1 or P2, depending on where this y is. And then the conclusion is this fibered Hilbert scheme has 2 components, C1 tilde, C2 tilde. The dimensions are 9 and 13 respectively. Okay, so these are the 2 moduli spaces in the first and the last chamber. And then I will move on to show you the intermediate wall crossings. So firstly, remember this is the picture of the entire wall crossing. I just show the 2 moduli spaces in the first and the last chamber. And then there are 2 more walls in between. And these 2 walls plus this third wall, the collapsing wall, are defined by these 3 Scherzak sequences of pairs. So then I will show the wall crossing, but I will do from right to left because meanwhile I can keep track of the curves. So I will first cross delta 2, and then we'll cross delta 1. And then finally we'll get this fibered Giesecker moduli. So let me start with crossing delta 2. Okay, 2 intermediate wall crossings. So when we cross delta 2 from right to left, and what happens is this component C2 tilde. So let's recall that C2 parameterizes a plane conic curve union a point. So when we cross delta 2, this component is blown down. I denote the blow down by C2 prime tilde. The exceptional divisor of this blow down, which I denote by D tilde, parameterizes all plane curves. So actually, when we cross the first wall, all the plane curves are removed. And then let me denote by D prime tilde for the contracted locus. So D prime, this exceptional divisor is contracted to D prime tilde. So when we cross delta 2, what happens is this component is blown down, and all the plane curves are gone. And then let me move on to the second wall crossing. So when delta crosses delta 1, and what happens is still the surgery is on C2 prime. So all the C2 prime is removed except for this new locus D prime tilde. Okay, so let me make a summary. So after these two wall crossing, and then delta will be lying in the first chamber. And then on one hand side, this moduli space is the fibered Giesecker moduli. And on the other side, we have this strata, in which the first part, which is an open set, still correspond to curves. And then the curve corresponding to this open set is the set of two skew lines. We have another locus D prime tilde, which is created by the first wall crossing. So the sheaves in the pair in D prime tilde is Giesecker semi-stable, but the stable pairs there don't correspond to curves. Okay, and then I produce this complete wall crossing picture, but due to my limited time, I will skip it. I will just spend 1 more minute. Sorry for that, I'm running over time. One of our original goals is to prove that the connectedness of Giesecker moduli space for rank 2, sorry, I forgot to say rank 2. The motivation was very naive because Harshun proved in his thesis that the Hilbert scheme of curves in P3 is connected. So we hope to prove that once we have this correspondence, we hope to prove that the Giesecker moduli space for rank 2 sheaves is also connected. But actually, let me put what I'm going to say in a remark. I think the idea in Harshun's proof is that he deformed any space curve into a planar curve, and then he proved that the part of the planar curve in the Hilbert scheme is connected. But I think this may not be applicable to the case of Giesecker moduli directly because a planar curve does not correspond to Giesecker stable sheaves. Or in other words, as I show in this example, and it holds more generally. So all plane curves are removed at the first wall crossing. So instead, we are trying to prove the following, that every wall crossing doesn't actually affect the connectedness. We're still working on that, but hopefully, if this were true, and then our idea is, so since the fibered Hilbert scheme is connected, and every time we cross a wall, the new moduli space is still connected. So finally, we get the fibered Giesecker moduli, which is also connected, and hence the Giesecker moduli is also connected. I think that's all. Oh, thank you.